Hello there. All right. I'm going to do two different examples of the area problems. I'm not going to do the one assigned in the homework because I want to give you a chance to do that one on your own to see if you understand what I'm about to show you here. So let's say we have a question where they tell us that they have $2,000 to spend, okay, on fencing material. And the material costs $1.25 per meter. Okay, so the first thing we need to do is figure out how many meters we have to work with. And so we'll do that by dividing these two. Okay, and that works out to be 1,600 meters of fencing. Okay, so sometimes they'll come right out and give you how much fencing you have or what perimeter you're working with. Sometimes you actually have to solve for it yourself. All right, then you have to be really careful because every question's a little bit different. When I give you questions like this on an assessment, they will always be a rectangular yard, okay? So you have various scenarios where you want to enclose a rectangular yard and you have to do so given a certain perimeter, okay? But your goal, again, because of quadratic relations, is to maximize the area. Okay, so the example that I kind of came up with here is you have, let's say, a farmer who has a rectangular field. All right, now, if the field was just rectangular, then the perimeter would be equal to 2 lengths plus 2 widths, right? And that makes perfect sense. However, usually there's some sort of twist in these questions. So the twist I'm going to add here is the fact that this farmer wants to divide his field into 3 equal sections, okay? So let's say one for his pigs, one for his goats, one for his cows. Who cares, okay? So now we have to adjust our formula because not only is the fencing going to consist of 2 lengths, but now we have 1, 2, 3, 4 widths to work with, okay? So that changes the question a little bit and you have to be careful. Sometimes the rectangular field will be divided into 3. Sometimes it'll be cut in half. It depends on the question. Now, this question, again, that I've made up, so don't be freaked out if you can't see it anywhere. The farmer wants to use his, let's say his farmhouse to enclose one of the sides. Okay, so we're not going to include one of the lengths in there. We can take that extra length right out of our formula. So this formula for perimeter, again, usually perimeter is equal to 2 lengths plus 2 widths, but then depending on the context of the question, in this example that I made up, we are not enclosing all 4 sides, right? And think about your backyard. Most of you don't have a 4-sided fence. You have your house here with 3 sides of the fence, okay? That's why we only have 1 measurement for length. And then again, because the farmer wants to divide his yard, we have 1, 2, 3, 4 widths. Okay, so the fact that we're working with 600 meters of fencing, that is our perimeter, and this is what we are enclosing with that perimeter. So all of these questions essentially follow the same sequence of steps. They're just going to change depending on the number you have for the perimeter and the way you are enclosing that rectangle. Okay, now our goal is to isolate a variable in this equation. I personally think it would be foolish to isolate W because I would move the L over and then I would have to divide everything by 4, creating a fraction or decimal. The far easier route is to isolate L. So the 4W is going to come over to the other side of the equation, change signs, and now I've isolated L. Okay, so again, first step, write your equation for perimeter. Second step, again, depending on the question, they're not always going to look like this. Second step, you're going to isolate either the length or the width. Now, our goal is to maximize area in these questions. Area of any rectangle, it doesn't matter if we took sides away. The area of a rectangular shape is the length times the width, okay? The reason we had to isolate L is because I can't work with a quadratic relation that has too many variables floating around, right? I need to have something squared. I don't have that here. However, when I isolate L, I am now going to kind of do a beautiful little throwback to unit 1. I am going to replace this L with this. So I'm saying the length is equal to 1,600 minus 4W. So I'm going to replace Okay, that's a really ugly 4, sorry. Woohoo! I am going to replace L with 16 minus 4W, and then this W is just gonna stay. And now this guy looks like a quadratic relation, okay? So from here, we could take many different routes. All right, what I'm going to do, just to kind of get organized, is show you how this is quadratic. I am actually going to expand, use the distributive property here. So I get 16W minus 4W squared. So all I did was multiply this guy by W and this guy by W. Now, if you're like me, this is making me nervous because it certainly does not look like standard form. I have to rewrite it in the correct order. Okay, so that is the equation for area, and our goal is to maximize this equation. So let's go through our options here. We have a quadratic relation in standard form. We want to get to the vertex, so we can either factor, or we could partially factor, or we could use the shortcut. Remember, the shortcut will not be an acceptable method to solve these types of questions. You could just use that to check your answer. So I'm actually going to go ahead and factor this because it is factorable. Okay, so we had the area is equal to minus 4W squared plus 1600W. Both of these guys are divisible by negative 4, right? Make sure you factor out the negative, right? We never want the coefficient of something squared to be negative. So negative 4W, I am left with W minus 400 inside the brackets. Now I'm going to set the factors equal to 0. I skipped a little step there, right? Kind of jumped the gun. Now I'm going to find my axis of symmetry. 0 plus 400 is 400. Cut in half is 200. So what does this mean? When I let the width be 200, I will maximize the area of my field. Okay? So again, this is my axis of symmetry. This is the value of the width. I'll go back to my diagram. Okay? I could make this anything. I could make it 100. I could make it 50. I could make it 20. And then I would have to adjust, right? Use my formula to solve for the length. But when I let this be 200, okay, I don't know what this is yet. I'm going to solve for it now. That gives me the maximum area, which is my goal. I want to maximize my area given a certain perimeter. So, okay, sometimes the question will ask for the dimensions. If the width is 200, we can now go back to this formula that we had earlier when we had isolated L, and we can solve for the length. And the length ends up being 800. Okay, so again, you could use various different combinations, but the combination that's going to maximize the area is when we let the width be 200 and the length be 800. We're not quite done solving the problem though, because we haven't actually solved for the max area. So initially, this was the formula we had. I'm going to go ahead and plug a width of 200 into that equation. Okay, and solve. And it works out that when I let the width be 200, the maximum area that I achieve is 160,000 meters squared. Okay, again, I don't have this question in front of me. I just kind of made it up. But let's say they wanted me to go ahead and express this relation in vertex form. I'm going to steal the A value from standard form. Okay, I can use W or X here. I think I'm just going to use X to be consistent, but the axis of symmetry, remember when we throw it into the brackets, it's like we're being lied to. It takes a different sign. So that's the axis of symmetry. That is the value of the width that maximizes area. And then my max area is 160,000. Okay.